Swayam Prabha. Digital India. Educated India.
Now we are going to use the relationships between the load, the shear force and the bending moment to solve a variety of problems. Now, similar to what we had done for the method of sections, we'll again travel from very simple examples to more complicated ones. And you will see that the real merit of using these relationships, maybe it won't be as apparent as you have when you are looking at the simple problems, but as you go more and more complicated ones, you will see that this method is highly efficient compared to the method of sections. Remember, for the method of sections, as we saw, that if you have a beam which with a variety of different loads, for example, if you have point loads, you have the distributed load, you have a concentrated load, you have triangular load, you have a concentrated moment, the number of sections, it keeps on increasing and increasing, and consequently the number of equations that you have to solve also proportionately goes up. Now in those problems you will see the real merit of using this relationship. But as it is, as how we do things, let's take a few of the smaller baby steps first, using some simple examples, and then we'll delve on to the more complicated one. So let's go ahead and look at the first example. So the first example which we have is this one over here. Now you might remember this problem, we had done this previously for using the method of sections, and if I just have to go back and show you that we had used the method of sections, where we took a at a certain distance we took a section X and we derived the shear force diagram and the bending moment diagram. Shear force diagram was linear, bending moment diagram was quadratic over here. The bending moment was maximum where the shear force was 0, and that was at a distance of L over 2, right? So we have solved this problem using the method of sections. Now let's go ahead and see that using the relationships how we are going to solve this problem. So we are going to use the relationships between the load, shear and the moment. Now before we go ahead and start using this relationship, let's maybe quickly write down again these relationships which we have. So the first relationship, if you remember, the first one was your dv dx was equals to minus of w of x. W of x is a function of the load that you have, right? And from here we also had another relationship, that is vd minus vc was minus of integral from xc to xt, which was the distance. Remember, these relationships are all derived by taking the distance from the left to right. So while in the method of sections you were, according to your convenience, you're taking a section on the left or section on the right, or a portion of the beam on the left, on the right. Here this relationship which we derived were always going from left to right. The point D was always to the right of the point C. You can use the relationship by going from right to left, but from the and for those, if you're going that way, the relationship, the signs and everything might change. So I highly recommend, when you use these relationships, you always go from the left to the right of the beam, and you will see that when you use this relationship, it really doesn't matter whether your structure load is complicated on the left hand side or it has more number of loadings. It really doesn't matter. It gives you a very nice way to solve the problem. So anyway, so going back over here, so we had wx dx, and which was again the negative of the, from this relationship over here, as you can tell, this is negative of the area of loading diagram. We had looked at one more relationship, that was between the moment and the shear. So let's just write that down as well. We had looked at our dm dx was equals to v, and correspondingly we had md minus mc, which was the area of the shear force diagram between C and D. So here also area of the loading diagram between C and D, right? And we looked at two more subset relationships, if you may, that for a point load, we expect a kind of a jump in the shear force diagram and no change in the moment, and for a point moment we expect a jump in the bending moment diagram, right? And no corresponding change in the shear. So these are the four things which we had looked at. Now, taking these ahead, let's try to draw the shear force diagram and the bending moment diagram for this particular beam that is there, right? So first of all, let's maybe just below draw two beams again, so that we know that where we are drawing the shear force diagram, and the another one maybe over here for the bending moment diagram, right? Okay, so let's take a look at this beam. So you have a simply supported beam with the reactions Ra and Rb, and let's say this load that you have over here, let's say this load is W, uniformly distributed load, so it's a constant, right? So let's start with the shear force diagram, or maybe even before that, let's write what our reactions are going to be. So your Ra will, as you can see, it's very simple. You can write W L over 2. Rb will also be equal, it's a symmetric structure, WL over 2 over here, right? Okay, so now for the shear force diagram. So for the shear force diagram, again, you're going from the left to the right. So when you're going from the left to the right, at the very left, I don't have any option but to have a vertical line of WL over 2, because that is the shear that you have over here. So I am going to go and I'm going to mark a vertical line over here as WL over 2, right? Now here kicks in the relationships that how the rest of the diagram is going to go. Okay, so for this problem, so let's just mark here. Okay, so for this particular problem, you see I'm trying to draw the shear force diagram. So this is my SFD again. So let's look at the relationships for the shear. So this is the relationship for the shear between the shear and the loading W that you have over here, right? Okay. First of all, we are hypothesizing that, or we have seen that our dV dx is minus of W, which is a function of x. Now in this case, that the W is just a constant load, so in this case equals to minus W over here, right? So this is degree 1, right? So sorry, this is a degree 0, not degree 1. So this is a degree 0, right? Because it's a constant line. So you can tell that once you integrate this one over here, that is, you find V, right? So V is going to be what? Once you integrate this degree 0, it is going to be degree 1. So V is going to have a linear variation. So it is a degree 1. So that means it is going to be a linear variation. Okay. So now we know that for this entire beam, the shear force is going to vary in a linear manner. So we have established that it's going to be a linear line, right? Okay. Now let's look at the second relationship over here, that is Vd minus Vc is negative of the area of the loading diagram. So at this left end, so we have 2 points over here. Let's just mark this. So this is my point A and this is my point B. So how can I write Vb minus Va? B is again the point to the right of A, similar to D, which was to the right of C over here. So Vb minus Va will be negative of the area of the loading diagram between B and A. So Vb minus Va, so B is here, A is here. So it is negative of the loading diagram between B and A. And what is the value? What is the value of the area of the loading diagram? The loading diagram has an ordinate of W and the length is L over here. Okay, so Vb minus Va will be equals to minus of W times L, right? Now that we have this over here, let's see from there, can we get what is going to be the value of the shear at the point B? Yes, I can, because I know the value of the shear at the point A is nothing but WL over 2 over here, right? So this gives me that my Vb minus WL over 2 equals to minus WL, which in turn gives me VB is equals to minus WL over 2. Right? So here at A, I have established, because of this reaction, I don't have any option but to have a pointed upward force WL over 2. And I have found out that at the point B, it is going to be a minus WL over 2 over here. So let's go ahead and mark that particular line as well. So at the point B, I am going to have a minus WL over 2. Now remember, the upper half is positive, the bottom half is negative, so I am not writing a negative sign over here. So I'm just going to write WL over 2. And what did I establish from here? That the variation of V is going to be linear. So from here to here, it is going to be just a plain and simple linear variation. So let's just mark that as well. So this is the linear variation that you're going to have. So here, as you can see from the figure, this is a positive and this is a negative. Now, as you can tell that here, from the symmetry itself, you can tell that this crossing at the 0 point over here, but the shear is 0, it has to be at L over 2. But this also you can derive from this relationship. So how can we derive that from this relationship? Let's take a look. So this is my point of 0 shear. So let me maybe go ahead and say this point as C for the sake of discussion. So I can write VC minus VA, right? The difference between C and A, the shear, difference of shear between C and A is going to be the area of the loading diagram between this point, between where C is and the left hand A. Now I'm trying to find where this C happens. So let me maybe call that distance as XC. So let me just mark that over here. So from here to here, let's say this is XC. This is what I'm trying to find. I know intuitively it's L over 2, but let's see if the equations give that or not. So VC minus VA, what is the value of the shear at C? It is 0. So this is 0 minus what is the value of the shear at A? That is W L over 2 will be equal to the area of the loading diagram between C and A. So what is that going to be? It is going to be W times XC, right? Because W is a constant, so XC may be somewhere over here. So W times XC, similar to what we wrote here before, it is W times L over here. So this is 0 minus WL over 2 is going to be negative of the area of the loading diagram between 0 and XC. So it is going to be minus of W times XC over here. So from that you can easily tell that your XC, that where the 0 shear happens, it is going to be come out as L over 2 over here, right? So this is also we sort of even intuitively, or if you want to go the hard coded way of deriving it, you can also derive. So we have this point C over here. So this is as L over 2 and this is also L over 2. So I am done with my shear force diagram. So you see, just purely using the relationships, I have drawn my shear force diagram. Okay, so now I am done with my shear force. Let's go to the bending moment diagram. So this is my BMD. So for that, I am going to use the relationships of the moment, or let me again draw a dividing line over here. So I'm going to look at the relationships of the moment. The relationship of the moment is dm dx equals to v. So let's just write that down over here. So I have dm dx equals to v, right? And here I have already established that v is the order of the it's a linear, it's a degree 1, right? So that tells me that once you integrate this guy over here, your moment is going to be a second degree, that it is going to be a quadratic, right? And also from our knowledge of when you have pins at the two ends and no externally applied moment, we know that the moment here is going to be 0, that is the moment at the point A is going to be 0, moment at the point B is going to be 0, and between A to B it has a quadratic variation, right? So let's try to find that how that quadratic variation is going to be. So if we have to find that one over here, so you see this is one relationship and the other relationship that you have is this one over here, right? So it is going to have a quadratic variation, and if it is starts from 0 over here, has a quadratic variation, and comes to this particular point over here, there is a point in between, it must have a maximum point, right? Now where does this maximum happen? Look at this relationship over here, and this will bring you back to what you had studied before. see dm dx equals to v, right? So the point where your v equals to 0, that is the point where your m must be maximum. So we can maybe write that over here. So where v equals to 0, it's a maximum or a minimum. Now we know that here it is going to be a maxima over here. So v, and I will tell you why it is going to be a maxima there as well, right? That why it is not in the bottom half plane. So for v equals to 0, so where then m will have a maxima, right? Now how do I know that whether it will be an upward quadratic or downward quadratic, like here? Remember dm dx equals to v, right? So at x equals to 0, what is the value of v? It is wl over 2. So it is going to have a slope somewhere something like this over here. Then at x equals to b, dm dx equals to the v at b, so which is minus wl over 2. So here also the slope will be something like this maybe. So in between you have the quadratic variation, and the maximum of that will be at v equals to 0. So that is at this particular point over here, at this point c. And let's calculate the value of what we get. So if this point is c again, where my cursor is at the moment, I can write mc. Let me write with the other color. I have mc minus ma here. md minus mc is the area of the shear force diagram between c and d. So here mc minus ma will be the area of the shear force diagram between a to c. So what is that area of the shear force diagram? It's going to be half of this one times this altitude over here. So it is going to be half times L over 2 times WL over 2. So that is WL square by H. So that is the MC. Why? Because MA equals to 0, right? Because MA is the moment at here where we have a pin. So the moment at A is equals to 0. So this is equals to 0 over here. So we have that MC equals to M max equals to WL square by 8. So let's just go ahead and draw that again. So this is, let me, as I said, it sometimes helps to draw these guidelines that we have over here. So my moment variation is going to be this quadratic, where here I am reaching the maximum value. So this is the max is WL square over 8, and as you can tell, the slope at this particular point over here is going to be 0 over. So you see, if you compare, let me write that a little bit below, maybe just not to interfere with what we wrote above. So M max becomes equals to WL square by 8. So if you compare the whole is positive, the whole diagram is positive over here. This is the positive shear, negative shear, the whole bending moment diagram is positive. Now if you compare this with what we had before, it's the exact same thing, WL over 2, WL over 2, positive, negative, you have a positive shear, and you have a maximum value here, WL square divided by 8. So I hope the first example using the relationship between the shear force diagram and the bending moment diagram was clear. Let's move on to the next example. This is the second problem which we are going to look at, and this is also you're familiar with. You have looked at this problem before. So we have a cantilever beam here with a triangular load Q, and Q say is a function of X, of course, right? And at the very right end you have a Q naught. So that kind of tells you that your Q of X is Q naught X. So it's a linearly increasing load from 0 to Q naught at the right end over here. And here I've taken the liberty to write the same relationships as we has before. So the more number of times you see the relationships, the more it gets into your head, and you kind of remember that what you are looking at over here. Now if you remember that this problem also we had solved using the method of sections before. If I just have to go to the previous page, this is what we had solved. We had taken section X and we derived the quadratic the shear force diagram, which came out as quadratic, and the bending moment diagram, which came out as cubic over here. So here this was our SFD and this was our BMD, right? So let's go ahead and now use the relationships to see that if we get the same diagram, same shear force diagrams, and or the bending moment diagrams or not. Okay, so first of all, let's again go ahead and draw the couple of beams which we always typically do to mark the different diagrams. So I'm going to use this beam for the shear force diagram, and I am going to use maybe this beam for the bending moment diagram that is there. So the first one is for my SFT and the next one is my BM. So let's go ahead with the shear force diagram first. So for the shear force diagram, as you can tell that here we are going to start with the relationships that is there. So we have this first relationship which we looked at over here, that our dv dx in this particular case is minus of, let's just write the general form first and then we'll write it to the problem specific, is minus of w, which is a function of x. In this case it is minus of q naught x by l, right? So now since this is degree 1, that kind of tells you that your v is going to be, v will be a second degree, right? And you can simply integrate this one as well, and you can maybe write the expression for v. So let's just go ahead and write that. So we'll get our v as negative of q naught x square by 2l, right? So we know that the shear force diagram, since v is quadratic, so the shear force diagram is going to have a quadratic variation from the left end all the way to the right end, because this load is a continuous load from spanning that entire beam that you have over here. Okay, so now at the left end, again going with our intuition, since this is a free end and there is no concentrated load, that here the shear force must be 0. So at this particular point your v is 0. So at a, so let's just mark it here. So this is my a and this is my b. So at a, shear force is 0. So va, we can say that equals to 0. And we know that the variation is quadratic, but let me ask you that what is going to be the slope at a? The slope at a, you see dv dx, the slope at a is going to be this value at a over here, because dv dx I can calculate anywhere. Right now at x equals to 0, which is at this particular point over here, it is going to be minus q naught times 0 by l, and which you can see from here as well. So the slope is going to be 0. So here you are going to have a 0 slope, right? Okay, now what is going to be the value of the shear at the point b? How do I find the value of the shear at the point b over here? Same, we can use this relationship which we have. So I'm going to write that as vb minus va is going to be equals to what? Is the negative of the area of the loading diagram between those 2 points. And what is that? It is the negative of the area of the loading diagram. So half times L times Q naught. Now here I know that my VA is 0 over here. So that kind of gives me that my VB is equals to minus Q naught L over 2. So at B, I am going to have a Q naught L over 2 negative. I'm drawing in the lower half, so I'm not marking with the negative sign. So, and what is the variation from A to B? You're right, the variation is quadratic, because I've already found this one over here. So this one means that it is a quadratic variation. So let's just go ahead and draw the quadratic variation like this over here. So this is quadratic. Now if I come and ask you that what is the slope of this line at B over here, very easy. This is the expression for the slope, and the slope of this line at x equals to L is nothing but equals to Q naught L divided by L, that is Q naught, which is this one over here, right? Because dV dx is simply the load, the negative of the load over here. So it is going to be minus of q naught. So let's just mark the slope here as well. So as you can see that it is a concave up curve. So your slope is